What is a wave? We're going to define a wave as a disturbance that propagates down some medium. So, for example, I have here a spring, and if I flip the spring, I can send waves down the length of the spring. Now, there are two things that a wave requires, one of which is a medium. By medium, I just mean it needs something to travel through. So here, in the case of my spring wave, the medium is just the spring. The second thing a wave needs is some sort of restoring force. Now, by restoring force, I mean that there is some equilibrium position. So for my spring wave, my equilibrium position is just the wave is flat here. And there's going to be some restoring force that wants to return it to this flat position. So the restoring force is some combination of gravity, which is pulling the spring down, gravity pulling the spring down, and also the spring itself, when it's stretched, has some tension associated with it. So it naturally wants to spring back down. There's something that's actually pulling it down. There's some tension within the spring itself that's trying to restore it to its previous position. When I have those two things, I have a medium that can hold some sort of disturbance, and then some restoring force that wants to restore the system back to its original state, away from that disturbance. That is how I get waves in a medium. Now, the long snake-like spring wave that I just showed you is a particular example of a wave called a transverse wave. It's called a transverse wave because the motion of the spring is transverse or perpendicular to the way that the wave moves. Here's what I mean by that. When I make my wave go, what I'm doing is I'm jerking the spring up and down vertically, but the wave itself is moving horizontally. So what's going on is that as I create this wave motion, the particles in the spring are moving up and down. They're moving up and down, but the wave is moving left and right. That is what I mean by a transverse wave. In addition to transverse waves, we also have a second type of wave called a longitudinal wave. Now, longitudinal waves are waves where the individual particles, the matter inside the wave, moves in the same direction as the wave. So here I have a slinky that's stretched out. If I just tweak my slinky, if I just give it a little push, I can send waves down the length of the slinky. So what's happening is I very quickly compress the slinky, and that pushes out to the coils that are further down along the slinky, so that the coils themselves are moving left and right. And the wave as well is also propagating left and right. Let's test the idea that waves need a medium. So I have here a bell jar, and inside the bell jar is just a ringer that I control from the outside by applying some voltage. You can hear that as soon as I apply that voltage, the bell starts ringing. We can hear it ringing. Let's see what happens when I connect a vacuum to this tube right here and suck out all of the air from the bell jar. It helps to go over a few different examples of waves. So we've already talked about one. That was the wave on a string or a spring. What are some other types of waves? Well, one of the most common ones is water waves. It's usually the first type of wave people think of when they think of waves. You also might think of sound waves. Sound waves traveling through air, although they could be traveling through water or some other medium. We could also talk about light waves. Light waves traveling through air, or in fact they can even travel through the empty vacuum of space. Light waves are a little bit of a different category. We'll talk about that in just a sec. There's also my favorite type of wave, which is the ballpark wave. Seems silly, but it is a type of wave. And so we can treat it very similar to the ones that we've treated, the other waves that we've treated. So we said that a wave requires two types, it requires two things. It requires a medium and it requires a restoring force. In the string or the spring, the medium was just the string itself, the material inside the string. For a ballpark wave, the medium is just you. You're the one who's going up and down. You're the medium for that wave. For water waves, the medium is just water. Traveling along the surface of an ocean or a lake or river, what have you. For sound, the medium is going to be, usually we think air, but it could be water, could be a solid. Could be lots of different materials that sound waves can travel through. Sound waves can travel through all types of different materials. Light is kind of a special case. So we normally don't think of space as being a medium, but as I said, light can travel through the empty vacuum of space. So a lot of time, for a long time, people tried to come up with the medium for light. They called it the ether because they just assumed it had to be there. There had to be this something that light was traveling through, and once they found it, they were going to call it the ether. Turned out that wasn't quite the case. So light's a little bit of a screwball in this list, for a lot of reasons, some of which we'll talk about later, of course. So we have these different mediums. We also need a restoring force, something that is going to cause the wave to try to snap back to some sort of equilibrium position. In the case of the string, we said that that was just tension, the tension in the string. In the case of ballpark waves, hard to say here, but I would say it's really just laziness. People don't like standing up for a long period of time, with their arms raised, so they get kind of lazy, they sit back down. For water waves, there's a couple of different things that could restore the water wave to its equilibrium position, one of which is gravity. We'll try to flatten out the surface of the water. Another of which is surface tension. So whenever you have a fluid, that fluid has some surface, there's some force that tries to keep that surface as small as possible. That force is called surface tension. So for waves that aren't too big, the surface tension will pull the water back to its equilibrium position. For sound waves, there is some pressure that causes the sound to restore to its equilibrium position. So as I am speaking to you now, my vocal cords are vibrating. They are shaking the air molecules, alternatingly compressing them and then rarefying them, making the air less dense. When they compress the air, while compressing the air back and forth very, very quickly, the compressed regions of air have regions of large pressure. That large pressure is going to push outward and try to restore it back to atmospheric pressure. What about light waves? Well, again, light's kind of the oddball case here. Restoring force, it's difficult to say what the restoring force for light is. I'm just going to put a bunch of question marks over there. Then we get into, is it a transverse wave or a longitudinal? Well, for a string, it really depends. Well, for a string, we're talking about a guitar string. that would definitely be a transverse wave. Because as the wave is going along, it comes up, if I'm looking at a guitar string, the wave is vibrating up and down, but the wave might be traveling left and right. For you, for the ballpark wave, you're going up and down, even though the wave is moving horizontally. So that would definitely be a transverse wave. Water waves are actually a bit complicated. In fact, despite the fact that it's the wave most of us are familiar with, water waves tend to be very, very complicated in their motion. As you get this sort of rolling motion of the molecules in the water. So we can't really call it transverse or longitudinal. Water waves are more complicated than that. But sound waves really are longitudinal. So when I speak la or sing, my vocal cords are vibrating back and forth. That pushes some molecules into some other molecules that get pushed down and down the line. Since the molecule is knocking into other molecules in the same direction that the wave is moving, we call that a longitudinal wave. So it turns out light is a transverse wave. How do we know this? Well, you may have heard light referred to as an electromagnetic wave. What that means is that there are electric fields and magnetic fields. And those electric and magnetic fields oscillate in different directions. So let's say the electric field is oscillating up and down like this, and the magnetic field is oscillating front and back like this. Well, the wave would travel horizontally, and it would be perpendicular to both the electric field and the magnetic field. And since the motion of the electric and magnetic fields are perpendicular to the direction that the wave propagates, we call that a transverse wave. Now we're going to deal with the mathematics of sinusoidal waves. Now, sinusoidal waves are a special case of waves where the shape of the wave happens to be in the shape of a sine or cosine function. I'm going to start here. We're going to define y to be the height of the wave. Now, when I say height, it could be the height of a wave on a string, could be the pressure of the wave, could be whatever the disturbance happens to be. Let's just assume it's the height of the wave of a string wave. So here, we're going to say that's the height of the wave at position x and time t. So my wave, if I look at a particular point on the wave, it's going to have different heights. It's going to go up and down over time, so I have to pay attention to not only where I am on the wave, but also at what time am I looking at that point on the wave. The A, we call that the amplitude. The amplitude is the maximum height of the wave. Okay, this is some code that I've written before. You can see we're focusing, we've highlighted the line a cosine 2 pi x over lambda minus t over t. That's the shape of my sinusoidal wave. I'm just going to go ahead and evaluate this part of the code, and you'll see we'll have something that starts to look like a wave. First thing I'm going to do is adjust the wavelength. Right now it's too small to see anything, so we're just going to make that wavelength a little bit bigger. I'm also going to adjust the amplitude. Right now the amplitude is 0. As I adjust the amplitude, you can see as the amplitude gets bigger, the wave gets much larger. And we have a cosine function. Here we have 2 pi. The x just tells me what point I am looking at on the wave, where in x, at what horizontal position x am I concerned with. Lambda is called the wavelength. The wavelength tells me the distance between the two peaks of the wave. Let's see what happens as I change the wavelength. You can see as I make it smaller or bigger, all it does is change the spacing between the peaks in the wave. Big T is called the period. That tells me the time it takes for one particle on my wave to start up, go down, and then come back up. Let's see what happens if I start off with a small period. If I animate that, you can see the particle jumps up and down quite a bit. It doesn't take very much time at all. Let's drag the period button. Let's make that a bit larger. You can see now the period is more reasonable. The particle bounces up and down at a decent pace. I'm going to go ahead and try making an even larger period, and we'll see that my particle moves very slowly. It takes a long time for it to go up and down. You'll notice here, between the x over lambda and the little t over big T, I have a plus or a minus. That tells me the direction that the wave moves. And it's a little bit screwy, because the plus, which we normally think means goes in the positive direction, actually makes us move in the negative x direction. This makes us move to the left. Whereas a negative sign, if I were to have x over lambda minus little t over big T, that would make us move to the right. Okay, let's just check and see if that actually works. I'm going to change that sign around. We're going to make that now a plus sign. It was a minus, we're changing it to a plus. I'm just going to scroll down. I'm going to turn up my wavelength again, increase my amplitude, give myself a reasonable period, and let's see what the animation looks like. We can see that with a plus sign in the wave actually moves to the left, not to the right. Because physicists are an argumentative group, we don't always agree on exactly how to write this equation. Now, we do agree what the equation means, but sometimes people use different names for different variables. It will mean the same thing, but it's a slightly different way of writing it, and it might be even a slightly different way of thinking about things. For example, we talked about that big T, the period, the time it takes for a part of the wave to go all the way down and come all the way up. Well, some people don't like talking about the period. They want to talk about it in terms of the frequency. How frequently does a particle go up and down? Well, it turns out the frequency, which we call f, or frequency, the frequency can be written as just 1 over the period. That's one way of writing the frequency. It turns out there's another way of writing this frequency. Because you see, we have a 2 pi here. And I have a big T, a period, in the denominator. So really I have a 2 pi over T. Now, sometimes physicists get lazy. They don't want to write that 2 pi over and over again. So instead, what they do is they come up with this other frequency. We call this the, sometimes you call this the angular frequency. Which can be written this way. It will be written as 2 pi over the period. Basically, I absorb that 2 pi and the period into one variable that we call the angular frequency. We can also write this as 2 pi times the frequency. That 2 pi can also get absorbed into the wavelength. So notice again, I have a 2 pi and a wavelength here. So sometimes you write this variable, you call this the wave number, usually gets the symbol k, which is 2 pi over the wavelength. All of these mean the same thing. They're just shorthands for writing the equation a little bit differently. And the problem is that no physicists agree on them. So we can interchange these. So for example, rather than writing this as y equals a cosine 2 pi x over lambda plus or minus little t over big T, I could write y equals a cosine, I'll absorb the 2 pi. I'll say that this is going to be kx plus or minus omega t. Some physicists like writing it that way because it's a little bit shorter. Turns out there's one more thing I can write. This one's kind of important. So here I have a wavelength, and I have a period. Well, we can write the wavelength and the period. We can relate those two things by the speed of the wave. So if I have my wave speed, it's not too hard to do dimensional analysis on this. I know speed has units of meters per second. Therefore, wave speed should have units of meters per second. And if I have a wavelength and a period, I can write that my wave speed is wavelength over period, or equivalently, is wavelength times the frequency, or equivalently, is the angular frequency divided by the wave number. All of these are different ways of writing the wave speed. Let's just put a box around these. What are the physical properties that wave speed depends on? Well, we might surmise that since a wave needs a medium, then it's going to depend on some properties of the medium. And that's correct. The first thing it's going to depend on is some property of the medium. How difficult is it to move that medium in the first place? So let's take the example of a string. I could look at the linear mass density of the string. Let's call that mu. By linear mass density, I mean how much mass do I have per unit length. So if I take a meter long string, how much does that weigh? So the units would be kilograms per meter. The other thing it will depend on is the restoring force. So what's the restoring force for a string? The restoring force for a string, we would suspect, is going to be tension, which will get the symbol big T. Let's try not to confuse that with the period. But the tension is a force, so its units are going to be newtons, or equivalently, kilograms meters per second squared. Now, maybe the wave speed depends on more than these things. Maybe it depends on more than the medium and the restoring force. But let's see if we can get something, let's see if we can get an equation that just uses these two things. So I want wave speed equals. Now to get wave speed, I need something that's going to have units of meters per second. So maybe I can get meters per second by taking mu to some power x times the tension to some power y. If I do that, I will get kilograms per meter, and I will get kilograms meters per second squared over here to the x and to the y. How can I combine these two quantities to give me something with units of speed, in units of meters per second? Well, let's see. Tension is the only term that has seconds in it. And it has seconds in the denominator and it's squared. But I want seconds in the denominator to the first power. I want a speed which gives me meters per second for the units. To do that, to get seconds in the denominator, all I have to do is take the square root of the tension. So that the y that I wrote down before is now 1/2. That would give me seconds in the denominator. I also know I need to cancel out this kilograms because there is no kilograms in the units for speed. So how do I cancel out kilograms to the 1/2 power? Well, I would need kilograms to the negative 1/2 power. So that my x would have to be negative 1/2. Does that give me the right units to the meters? Well, in the brackets, the meters are in the denominator. If I take that to the negative 1/2 power, the negative flips the fraction upside down. So that would mean the meters are up top, but it's meters to the 1/2 power, not just meters by itself. But I also have this meters to the 1/2 power. So I have meters to the 1/2 power from this term, meters to the 1/2 power from that term. Lo and behold, I get meters by itself, meters to the first power. So if I take this formula, I will just get the wave speed. I will get that the wave speed equals the tension divided by the mass per unit length, whole thing taken under a square root. What exactly do wavelength and frequency mean for sound waves? Well, I've got an audio speaker here and a function generator here. I can use the function generator to produce different frequencies of sound coming out of my speaker. Let's see what happens to the sound as I change the frequency. From this, we can see that the frequency of the sound correlates to the pitch, with higher frequencies giving you higher pitches of sound. So what exactly do wavelength and frequency mean if we're talking about light? Well, to test that, we have here 3 solutions. I've got a red solution, a green solution, and a blue solution. And we're going to look at the absorbance spectrum of each of these solutions using the UV visible spectrometer that we have in the basement of Carver Lab. Here we go, starting off with some red solution. Take some of this, turn on that there. Take our red solution, put it in the UV vis, and we're just going to scan that. Okay, we now have data, and you can see we have data for each of our 3 samples. Now, what I want you to do is see if you can figure out which sample is which. So sample A is the gray curve. It's got a peak around 500 nanometers. Sample B is the brownish looking curve. It's got a peak around, looks like 630 nanometers. And we've got sample C, which is the black curve, which actually has 2 peaks, one around 400 nanometers and then another around 630 nanometers. So which sample corresponds to red, which corresponds to green, and which corresponds to blue?
Now, to help you out with that, I will remind you that the visible spectrum runs from 400 nanometers to 700 nanometers, with 400 nanometers being the violet, 700 nanometers being in red. Anything below 400 nanometers is ultraviolet, so that's UV, that's out of the visible spectrum. Anything above 700 nanometers goes beyond visible light as well. That's going to be in the infrared. So with that in mind, let's see if we can figure out what each of these samples is. So let's pick an easy one to start with. Let's use sample B. It's only got one peak, a very sharp peak around 630 nanometers. So do you think the curve with an absorbance peak around 630 nanometers is going to be red, green, or blue? Now, you might be tempted to think that since sample B has a peak with a large wavelength, that perhaps it will be red, because after all, red is the largest visible wavelength we can have. Maybe sample B will be red because it peaks in the large wavelengths. However, this is an absorbance spectrum, which means these are the colors that are being absorbed. So we are going to see every color but red. For this reason, sample B, the brown curve, is going to be not red but blue, the furthest color away from red, because we're absorbing the red light. Similarly, if I look at sample A, which absorbs far away from the red, we can see it's absorbing the blue and violet colors. This means that sample A is going to appear red because all of the blue, violet, and other low wavelength colors have been absorbed. Only the red 600 to 700 nanometer light is going to pass through. By process of elimination, sample C must be the green sample. So what's going on here is we can see there are two peaks, one in the red, one further out in the blue and violet. There's a narrow dip in the middle which allows the green light to pass through while the red, blue, and violet light gets absorbed.